Good day, and you're all most welcome to today's technical session of the CNPS. Today is the 28th of March, 2026. Now, something a little different today, actually. We're delighted to have Dennis Allen and David Bauer, who have done some work on furthering the analysis of Neo-Newtonian mechanics, actually. So when we talk about things like Neo-Newtonian mechanics, we're frequently concerned with dynamics and inertial systems and so on. But today, Dennis and David have actually applied the Neo-Newtonian principles of mechanics to electromagnetism. And the application of such mechanics to correcting and improving analysis of what they say, the analysis of electromagnetic momentum and electron inertia. Yes, and there's also a key paper which we'll be referring to, or they'll be referring to presently, produced by a gentleman by the name of Kulwick in the 1950s. So they'll be looking at that. They've done a lot of work, actually, both calculation and conceptually. So so basically what we'll do is they've given me a lot of information. We have actually 8 papers there. One is basically slides, and I think they'll be going through that. I think maybe David may be speaking to those. But I'll introduce or I'll bring up Denny first, Dennis Allen. And people are coming in on the Facebook and YouTube. So again, feel free to post any questions you wish. But on the social media, most people are conversing between themselves, which is fine. We've no problem with that. But I may miss it if you have a specific question. So do say specific question for the speakers today, or maybe even for me, and I'll deal with that later. And then we should have people coming in on the green room. We actually only have one at the moment, but we should have people coming in. Some people go through the talk through the social media, and then when we finish the talk, which is about an hour, roughly an hour, they go in on the green room. So the green room gives us a possibility of a sort of a one-to-one back and forth conversation, and that should be interesting. So without further ado, I'm going to bring our gentleman up. There's Dr. Dennis P. Allen Jr. and Dr. David M. Bauer. I take it I'm pronouncing your surname correctly, David.
Right. It's not the German B-A-U-E-R. It's Bauer.
Yeah, but it's pronounced the same way.
Right.
Okay. Perfect. Now, let me see the mechanics of this. So the first thing, I'll just bring the slide up because I have it here. Let me see now. Yeah. So what I'll do is I have control over this, and if you want me to bring up the papers for illustrative purposes, I'll do that at any time. So I'm at your beck and call, but I will disappear myself. I'll bring my photograph off, and if there's any specific thing, there might be delay in my coming back because I'm actually not part of the proceedings and I'm mute. But I will come back at any time, and I'll leave the two of you gentlemen up. So Denny, I think, is going to introduce the whole proceedings, and then I think he's going to hand over to David, who's going to go through the slides. But just tell me at any time if you want me to stop, if you want me to pause, if you want me to bring any other document up. Okay.
Okay.
But apart from that, I'm disappearing now. I'm going off the screen. So the floor is all yours, gentlemen, and in particular, Denny, to say a few words of interest.
Well, the key to my thinking is variable inertial math. We know from relativity that mass does vary. If although there are alternative ways of looking at it, and the mass is a function of the acceleration. It's not generally realized that, but you have the gamma factor if you accelerate straight forward. But if you accelerate sideways, you get a different factor. So, in other words, the mass gain depends on which direction you accelerate in. If you're going at a relativistic velocity and you accelerate straight forward, the gamma function, the gamma factor applies. But if you accelerate sideways, the same acceleration, you get a different factor. They don't talk too much about this because they like to think that mass would not depend on things like that. But it's a matter of record that that's the case. They believe that. And so I've just taken that a little further and said not only is mass a factor of velocity, but it's also a factor of acceleration. And not just acceleration either, but also this time derivative acceleration. And here we have acceleration vector and time derivative acceleration vector called the jerk vector or the surge vector. And so that's my idea, is to introduce variable inertial mass, not only for velocity, but also for acceleration. And in a way that's a nonlinear acceleration increase, so that the acceleration doesn't go up in a linear fashion. And this is important because Professor Alexander Dmitriev of Russia, he's from the Baltic State University in St. Petersburg, has done some spinning rotor experiments. And he noted that there's weight loss if you weigh the rotor as it spins, and as it runs down, you get less and less weight loss until it drops to zero. Now, this is important because it falsifies the equivalence principle, which is the very heart and soul of general relativity. And his dream is to be the one. He's about ready to retire. It's my age, about 83. He's about ready to retire, and he wants to go down in history as the one who shot down curved space-time and general relativity. But his problem is that the experiments he'd done, the weight loss is so small that it's hard for him to get people to believe it's real. It's just not an apparatus effect. But he keeps on working. He keeps doing these experiments. Now, why don't we go through the slides?
Okay, I guess it's my turn. I just want to give a few disclaimers. My name is David Bauer.
David, I'm sorry to interrupt. May I just ask you, some people have suggested that the left-hand side of your slides, if you could get rid of the right-hand side, it may be easier to read. Is that an option?
I'm using a Beamer slides from LaTeX. I think they're a lot superior to PowerPoint. Is it, I'd have to go back and reprocess it just to get the slides.
Okay, we'll leave it.
Okay, yeah. I'm sorry, I didn't even think about that. But you can process it just to get the notes or just the slides or both. I've given you both. So I apologize for that. But anyway, my disclaimer is that I was just basically asked to help Dennis with the preparation of this talk. I'm certainly not an expert. I view myself kind of like in the role of a graduate student who's just kind of learning the topic. So I apologize for that. I'm not an expert, but I will go through the information that which Dennis has given me. Today we're talking about the basic theory of Neo-Newtonian mechanics, which Dennis did develop. He did develop this theory. We're also going to be talking about some applications in correcting Kowick's electron current model. If you look at the next slide, it has this and some future topics. Bergson-Allen electron theory and its extension to neutrons and the electron-positron ether, and inertial propulsion, reactionless drives. I got interested in the inertial propulsion, whether it's really true or not. I've seen some videos of people showing these inertial propulsion drives, and there's a big, huge debate about whether these are actually true reactionless drives or not. Maybe we can talk about that in the future. The next slide shows some references. Why don't you go down to the next slide, the references. Ian, can you show us the...
I'm just coming back for a second because I'm having some problems. When you say next slide, do you mean the bottom here or do you mean the next physical slide?
Yeah, just the one that says references. So your screen can show not only one slide, but a couple of different slides.
Can I scroll down? Because I'm having difficulty. I have to open the thing again. Let me see now. Okay, here it is. It's having trouble there. Slides, here we are.
Oh, now you can scroll. Okay.
So I can scroll, but I have to open my own application, which means I'm cutting off my own screen. But you just tell me if it's working. So you want me to scroll down further to references?
Yeah,
there.
yeah.
Is that it?
Well, so we see the references here. So there's like 5 references. Of course, the original book, which Dennis Allen wrote in conjunction with Jeremy Dunning Davies, which explains the theory. Then there's the important paper by Kowick, which we're talking about today. And then a little one-page communication by a guy named Achilles. And then we have 2 Dmitriev papers, one talking about hitting a ball against a massive plate and one talking about the weight experiment with the rotor, which Dennis just spoke about. So those are some of the references. I think at the end, you can have the people who are watching can have a chance to email in and get copies of these references. Okay, scroll down to definitions. Okay, so here I've just given some definitions of different quantities. It should be pretty self-obvious, pretty self-evident. V is just the magnitude of the velocity vector. A is the magnitude of the acceleration. Then we have a new vector called the jerk vector, and we call that S. That's the change of the acceleration with time, and S is the magnitude of that. And then, of course, we have our little g, which everyone should know. It's the gravitational force. And we also introduce an angle, alpha, as the angle between the acceleration and the jerk vector. A little while later, we're going to talk about the force of gravity, and here we have the usual constants. Big G, the Newton's gravitational constant. Big M, little g represents the gravitational mass of the Earth, and R is the radius of the Earth. So those should be pretty self-evident. And then if you scroll down again, we have some more definitions. Now here we have the mass change function, or F. Dennis, is that what you call it, the mass change function?
Yes, that's right, David.
Mass change function. Okay, so I like to be perfectly clear in my equations. So I've written it 3 different ways, and it's pretty obvious what I'm doing here. C and K are just constants. A, S, and alpha I've described already. Then I've just regrouped them and let A represent A times S times cosine square of alpha. Pretty self-evident there. Now, Dennis makes this comment that C vanishes if we have right-left asymmetry, so it doesn't matter which way the rotor turns. Now, we're particularly talking about gyroscopes here rather than other types of masses. So this work is mostly related to gyroscopes. And of course, a rotor can spin either clockwise or counterclockwise. All righty, let's go to point number 1, introductory observation. You just scroll down a little bit.
Sorry for the delay, because I'm losing. I have to go back to where I found the thing. I'll have it for you for a second now. Yeah. Okay.
Okay, great. Point number 1, introductory observation. We'll begin with this Russian Dmitriev. As Dennis Allen just mentioned, he observed a small weight loss in horizontally rotating cylinders. He claimed this was due to gravitational mass reduction. He has an interesting theory. I tried to read his paper. He talks about gravitational induction in the same way that Lenz spoke about an electric current loop would try to maintain a constant flux through it, even if the current is changing, increasing or decreasing. He said that there's an induced force on any type of mass that's changing or dropping or falling or going up. There's an inductive force acting to counteract that. So he tried to explain this weight loss in terms of gravitational induction. And at first I thought he was trying to invoke some sort of gravito-electromagnetism, like the theory that Heaviside talked about. He said that gravity has a magnetic analog, but it's much simpler, his concept. But anyway, Dennis Allen had a new way of interpreting this. He said, if the gravitational mass remains the same, but the inertial mass of the rotors were increased, then the upward inertial force would push harder and cause apparent weight reduction. Now, this concept is related to something I first came across in reading Assis's works, where they imagine that the inertia of a body is due to a so-called inertial force. So you almost like take away the mass of the body, consider it massless, and just say that the effective inertia is due to an inertial force. So if you have a body falling in a gravitational field, the inertial force would be counteracting the gravitational force. Does everyone follow what I'm saying?
Yes.
And as Dennis, that makes sense, right? Am I explaining it correctly?
Yes.
Yeah. I was very puzzled when I first read that in Assis's work, but now I understand it. So this calls attention to the fact that inertial mass and gravitational mass may be different, which just invalidates Einstein's equivalence principle. By the way, I did discover in my reading that Einstein's equivalence principle, the whole thing where you have an elevator being pulled upward in outer space, accelerating, well, say like it's accelerating to the right, is equal to a gravitational force in the left direction. Einstein said that was his happiest thought of his life, but that's only half correct. Did you all realize that? That if you use that to predict the bending of light in a gravitational field, that gives only half the correct answer. So the equivalence principle is wrong for many different reasons. Another reason the equivalence principle is wrong is because of tidal forces. The gravitational force of the Earth is spherically, is radially well, it expands as a sphere. It's not perfectly uniform, so it introduces tidal forces, which can allow you to distinguish between that. Am I making sense? Is everyone following what I'm saying?
Yes.
Okay, let's go on to point number 1, continued. So let's put some numbers to this, or put it in equations. Consider an object with inertial mass m sub I and gravitational mass m sub g falling due to the action of a gravitational force g. This situation is simultaneously described by the two equations. Well, there you have 1 and 2. G that's our typical Newton's equation, where I've just written it as a scalar. I've written the scalar part of it. The magnitude of the downward force is equal to Newton's constant times m little g, big M little g, divided by the radius of the Earth square. And obviously this only is valid close to the surface of the Earth, where the gravitational force doesn't vary very much. But now we also have that g is equal to the inertial mass times the acceleration in the downward direction. And so if you put those two together, that implies the right-hand side of 2 equals the right-hand side of 1. And that's what you get, equation 3. So let's go down to point number 1, continued. So we have this equality. Now let's consider 2 cases. If the inertial mass equals the gravitational mass, then we have our usual derivation that the acceleration is equal to big G, little m g, big mg divided by r squared as usual, which gives us the value 9.8 meters per second squared. All right. However, if the inertial mass is greater than m sub g, then a sub I is less than this. And so the object, which we're considering a spinning gyro, falls more slowly, i.e. with less acceleration, because a sub I is the actual observed acceleration of the gyroscope when spinning. And the right-hand side of the equation immediately above is the gravitational acceleration in the absence of spinning. So we have 2 cases. We have a gyroscope that's spinning. Its gyroscope that's not spinning is falling with 9.8 meters per second squared acceleration. The gyroscope that is spinning is falling with less acceleration. Okay, any questions or comments on that? Is that logical?
May I just come in with a little bit of pedantry? I think it doesn't affect your argument. Your argument is sound, but dimensionally, you shouldn't have that mg on the right-hand side. I think. Just get the thing back again now.
On the right-hand side of what?
So say you start from the beginning. Let me see now. Let me see where you start there.
Yeah, but Newton's laws
So
involve
that mg should not be there.
Why?
Let me see now. Dimensionally,
Newton's constant takes care of all the dimensions.
Well, yeah, but is G acceleration or is it downward force?
That's a force there. That's a force.
That's a scalar. That's a scalar equation.
Yes, but G.
Yeah, but the dimensions of that are force, and you'd have to multiply that by m to get force. So I think it should be just G, capital mg over r squared.
G is the magnitude of the force.
G is a force, not an acceleration. He's using a different notation. G is a force.
G is the absolute value of the vector G.
Okay, it's probably not worth arguing about because I think your argument is sound. But I thought that was the acceleration due to gravity, and that's the gravity.
No, that's the force. Well, that's the force. Yeah, okay. Yeah. Maybe I'm using it inconsistent with the. Yeah, mg is the force of gravity, which is 9.8. G should be in newtons, but.
It would have been better if you hadn't
go-
used G there. Yeah.
If you go back and look at my definitions, I say that little g is the magnitude of the gravitational force, not mg.
Yeah. So,
See, look at the next.
That's correct.
The next equation, g
One and
equals
two
m sub I
apply
a.
that. Yeah.
Look at g equals m sub I a. That shows you that g there is a magnitude of a force.
Yeah, it would have been better if he hadn't used G there and some other letter, because G is, most people think of G as 9.806 meters per second squared, which is an acceleration. But he's using it as a force.
Okay.
Yeah. Point
Okay.
well taken. Point well taken. Yeah.
Thank you.
Good point. All right, let's so go back to point number one continued there. Okay, so we agree with this?
Yeah.
Okay, let's go on to point number two. So thus we describe the inertial mass gain of our Neo-Newtonian mechanics by noting that it can be explained as a dynamic inertial R mass, m sub r, defined by m sub r equals m times a function, well, m is the mass, times a function of acceleration and jerk, where m is the inertial rest mass. We can call that the invariant mass. A is the acceleration vector, dA dt is a jerk or surge vector, f is the mass change function. But since all directions in space seem to have the same properties, we can write m sub r equals m times f of a dA dt sine alpha, where A is, well, I'm just repeating myself in these definitions. Alpha is the angle between vector A and the jerk vector. So we've defined this new thing called m sub r, the R mass. Dennis, why did you call it the R mass?
Well, originally I thought it was going to be a reduction in inertial mass, because Lathwaite claimed that he observed reduced inertial mass. But
R mass, okay.
so I called it m sub r, meaning reduced mass. But then I found out that Lathwaite had it backwards somehow, and it actually increased. So, but by that time it was too late to change.
I would tend to look at R mass and think of that as rest mass. But anyway, we'll continue with m sub r. I like it. Okay, let's go to point number three. If we reformulate elementary Newtonian mechanics using inertial mass gain, we find, using Dimitriev's ball against a massive steel plate experiment, and the paper is referenced above, that d m sub r v dt equals m sub r a without the extra term on the right, so that d m sub r dt equals d product m sub f, m of m and f dt equals f dm dt, even if f may be changing with time. So I think this is your sleight of hand, Dennis, that you found, right?
Well, what do you mean sleight of hand?
I mean, this is your mathematical trick.
Yeah, well, I found out that the mass, so you can look at the m sub r, the R mass, as 1 plus some positive quantity times the inertial mass, the rest inertial mass. But it turns out that Newton actually supposedly took the time derivative of the momentum, which was inertial mass times the velocity, and so we got two terms because usual definition of derivative.
Right.
One was the force, and the other was the change in inertial mass due to the change in time times the velocity. And this comes into rocketry, because as the rocket expends its fuel, it becomes less massive. So you have to use both terms to model a rocket traveling. However, the second term doesn't come up in anything but the actual inertia, actual rest mass. But if we subtract from the R mass the rest mass, then we get what we call the pseudo mass, which doesn't have the property that when you differentiate it, it becomes has a time derivative of the pseudo mass vanishes, even though the pseudo mass may be changing in time. That's why I have to call it the pseudo mass, because it doesn't behave like ordinary inertial mass, where, according to Newton's equation, the time derivative of the momentum is force ma plus dm dt times v. The pseudomass does not obey that two-term derivative when you take the derivative of the velocity times the r mass, or the pseudomass. So that surprised me, but it's not the end of the world. It's something that I got from an experiment, and I just had to conform to it.
Yeah, so this definition of force in terms of change of momentum with time is and following through on the differentiation, you get the two terms. That's where you get this longitudinal mass and transverse mass, which, by the way, Einstein got that wrong in his first paper. Were you aware that he got that wrong?
No.
Yeah, the longitudinal mass is gamma cubed times the mass, the rest mass, and the transverse mass is gamma times the rest mass. Einstein had gamma squared gamma squared m for the longitudinal mass. But anyway, that's one of many mistakes that Einstein made. Okay, let's go on to point number 4. Ian, it looks like you got rid of that side panel. That's good. Okay, we next expand this mass change function in a Taylor series in the 3 variables a, dA, dt, and sine alpha, and show that f equals 1 minus this constant times a, dA, dt, cosine squared alpha for situations that are left-right symmetric, and for constant k less than 0, which must be experimentally determined, of course. And so we see that there are 2 effects: a generalized nutation weight loss effect and an inertial mass gain effect, with the former larger than the latter in Dimitriev's work. But the latter, being a nonlinear acceleration effect, hugely applies to electrons that are only of the very small inertial mass of about 9.1 times 10 to the minus 31 kilograms. And so by Newton's second law, since therefore F divided by m is equal to a, thus a is almost infinite because m is almost 0. Okay, so let's go to point number 5. I'm gonna go get this paper by Kolwick. I left it right up here. We want to transition into this paper by Kolwick entitled "Electromagnetic Momentum and Electron Inertia in a Current Circuit." And basically, Kolwick is saying that Maxwell postulated these inertial effects of the electron current. Well, first of all, Maxwell was not convinced that the current was composed of these discrete charges, right? He wasn't convinced, but he said if electric current was composed of these discrete charge carriers, there would be momentum effects. But these momentum effects were never found. So how do you reconcile that? So I want to read the summary and the introduction of this paper very slowly so that you get the gist of what's going on here. Summary. In the second volume of his Treatise on Electricity and Magnetism, Clerk Maxwell developed the theory of electric current circuits from general dynamical principles and discuss the experimental effects which should occur if an electric current is a true motion of some substance possessing inertia. Since none of these effects had at that time been observed, Maxwell developed his general electromagnetic theory on the assumption that they do not exist, or at least that they produce no sensible effect. Okay? Now remember, he didn't have a concept of these small little electrons. That was introduced by Lorentz. I guess the idea that electric current was more like a fluid of some sort. But still, a fluid can possess inertia. Second paragraph of the summary says, it is now known, however, that an electric current in a conductor consists of moving electrons, and the inertia effects which were discussed by Maxwell have been observed experimentally. They are extremely small and have not been brought within the scope of electromagnetic theory. A conduction current is usually assumed to be due to the drifting along the conductor with a very small mean velocity of all the available conduction electrons, so that the kinetic energy of the electrons due to this motion is negligible in comparison with the magnetic energy of the current. Electron inertia effects in current circuits have therefore been accepted as somewhat outside classical electromagnetic theory, a position which is illogical if, as is usual, we identify the kinetic and magnetic energies of a free electron. It is shown in this paper that it is possible to identify the kinetic energy of the conduction electrons in a current circuit with the magnetic energy of the current, so that electron inertia effects can be included in the general electromagnetic scheme. In consequence, a current circuit can be said to possess an electromagnetic mass whose motion when current flows implies or entails electromagnetic momentum. This momentum accounts for the known effects of electron inertia and also for the force on the end wire of a long rectangular circuit. The relativistic form of the theory indicates the possibility that electromagnetic laws may depart from the classical form, becoming nonlinear in circuits where a high inductance per unit length of conductor is combined with a current greater than is usually found in practice. The inadequacy of the classical theory also extends to the known electromagnetic properties of superconductors, and the present hypothesis suggests the possibility of a unified theory in which there would be no necessity to distinguish between a superconductor and a perfect conductor. Okay, that's the summary. Any comments on the summary?
Well, these effects that he's finding are very tiny, and so you might say they're not too interesting. However, along the way, in finding these effects and verifying them, he shows something remarkable, or attempts to show something remarkable, and that is, if you have electrons flowing down a wire, that the magnetic field around the wire is due entirely to the spinning magnetic fields of the individual electrons as they go down. It's not the charge that goes down the line, but it's the electron magnetic fields that cause the lines of force to circle the wire. And today, as far as I can tell, it's believed there are two sources of the magnetic field around the wire. One is the charge going down the wire, according to Maxwell, and the other is the spinning of the electrons, which then are little tiny magnets, which is a lesser effect. That's, as far as I can tell, that's the way it is. Now, he points out that, and he tries to point out anyway, that no, it's all due to the electrons spin magnetic fields. And so this is quite a result. I think it's far more important than worrying about little tiny inertial effects. And but it was discovered in trying to nail everything down perfectly and revise Maxwell's theory in the light of Newtonian mechanics and Newtonian mechanics applied to electrons. But he ran into some trouble.
Dennis, let me just stop you for a second. So you have a long straight wire with a current flowing down the wire. We know that the magnetic field circles the wire. It forms concentric circles around the wire. And this has been attributed in thousands and thousands of physics textbooks as due to the electrons slowly traveling down the axis of the wire. Is that correct?
Yes.
But what you're saying is that the electric field is really due to what? Helical motion of the electrons or something like that?
No, the magnetic field. The magnetic field.
The magnetic field. The concentric circles or magnetic field is due to what?
It's due to the fact that the electrons are spinning charges, and so they generate a current, which then gives a magnetic field. And so they're little magnets, they're little cylindrical, according to Kowick, they're little spherical magnets. But this idea, though interesting, his approach has three main flaws to it, which I'll go into in a bit. But he's trying to show along the way that it's not the charges moving down the wire, it's that the charges moving down the wire are spinning, and therefore they have a magnetic field. Go ahead, David.
Well, yeah, but wouldn't, if you had a wire without a current going down the center of it, wouldn't the electron still be there and still spinning, and wouldn't it have a magnetic field around it?
In things like iron, they have domains and so on of magnetic lightness, I guess you'd say.
Right.
But ordinary conductors like copper, the free electrons, if there's no electric field, no magnetic field other than them spinning, don't tend to line up really. They're sort of because of there's heat inside the wire, and so
they jiggle around
and so on. They're sort of they average out to zero.
Right. But if you have copper and then you apply a little electric field to it, it causes all the electrons to align, and their spin magnetic field aligns and causes the greater magnetic field around the wire.
Well, it's not greater. It's entirely due to them, according to Kowick.
The sum it causes the electric field that you apply on a conductor causes the electrons to align, their spin axis to align, and that causes a summation of these electron spins.
Yeah, but it's a little more complicated. That's basically right, but it's a little more complicated because if you look at the Achilles paper, which modifies Maxwell's equations a little bit, based on an argument of Einstein, it starts out. Unfortunately, I don't have a copy of that right here, but we'll hopefully get to that in a minute. The electrons, as they go down the wire, are actually spiraling. They're not going straight down. They're spiraling with the center of the spiral being the center line of the wire. Oh, here we go. So you can see in the diagram in the upper right-hand corner, they introduce a test charge, and if the magnets are rotating, it affects the test charge differently than if the magnet is not rotating about its axis of symmetry. This is surprising because if a magnet is disk symmetric or cylindrical symmetric, if you like, then you can't. The magnetic field will not depend on the degree of rotation, whether it's zero or no matter what it is, within limits. But if you introduce this test charge, you see that the spinning of the magnet does affect and doesn't generate an electric field depending on how fast it's spinning. Now, this is related to the Faraday paradox, where he said that if you spin a bar magnet about its axis of symmetry, do the lines of flux rotate or not? Well, according to Achilles, yes, they do rotate, and that's the effect he's trying to diagram in the upper right-hand corner. So then if the magnet spins about its axis of symmetry, the amount of electric field generated near it is related to the spin. If it's zero, the electric field is zero. If it's high, the electric field is high. And so this is, if you do the math, vector math, you can see that this means that the electrons going down the straight cylindrical copper wire have to spiral down. They don't go straight down. And the spiral is very, the torsion of the spiral, if you know what torsion means, is very small compared to the curvature of the spiral. And so I got this diagram here, which I should have scanned into my computer, but I forgot to do it. Can you bring that up, Ian?
It's also very rich, but it's good fat and protein.
Ian, can you show the thing that Dennis wants to?
Yes, I'm trying to now, David. I don't know if it's big enough to see there. We can maybe maximize it. There.
Yeah, we see it, Dennis. What did you want to point out?
How the spiraling down the wire generates the circular magnetic concentric circles of magnetic flux about the wire.
Hold it up again.
See, it shows the wire, which is the big circle, a cross section, and then one of these electrons, which is spin toroid of charge, not a sphere.
Yeah.
And you can see that the part of the magnetic field that's outside the wire is pointing downward, and the part inside is pointing upward, because the lines of flux have to close on themselves.
Right.
So there's a this is a cross section. That means
right. It would cause circles, concentric circles around. If you extended that around the circumference of the wire, it would produce concentric circles of magnetic flux. I see that.
Yeah.
The lines inside the wire would cancel.
Yeah, and the lines outside would be in the opposite direction of the spin, the circulatory motion. So anyway, I'm sorry about that. I should have done that yesterday. Didn't think of it.
Very, very interesting. Yeah. Very, very nice. Do you want me to read the introduction? The first
Go ahead.
All right. It is a common practice in electromagnetic theory to regard the magnetic energy of a current circuit as electrokinetic and to compare the expression 1/2 Li squared with the kinetic energy of a moving mass, 1/2 mv squared. It is the purpose of this paper to show that the magnetic energy of a current circuit can be identified with the kinetic energy of the mass equivalent of the total electromagnetic energy of the conduction electrons. The concept of the electromagnetic momentum in a current circuit will then be used to determine the force on the end wire of a long rectangular circuit and to bring the known effects of electron inertia in a circuit within the scope of electromagnetic theory. So, and he almost achieves this, but he's using a bad or an incorrect version of the electron, which he models as a sphere. Is that correct, Dennis?
Yes, and he apologizes for that too. See if I can find it here. Yeah, on page 161. Can you bring up, okay, page 161, near the top left. Yeah, he says, since we assume that V is small compared to C, if a charged sphere is stationary or moving with a velocity V less than C, that's not what I want. Okay, yeah, if a charged sphere is stationary or moving with a velocity V much less than C, if the charge is uniformly distributed on the sphere, the energy of the electric field is easily found to be, and it gives a formula, which is the mass equivalent he divides by C squared. Plus, M sub G is equal to 3/4 M sub E. So that if an electron is to be regarded as a spherical aggregate of charge, whose mass is entirely electromagnetic, it is necessary to postulate additional electromagnetic energy, and he gives some formula. It is well known that a stable spherical electron cannot exist without internal forces in addition to those of classical theory. Equation 20 may be taken to represent the energy of the non-classical and present unknown forces which keep the electron from exploding. So in other words, he's saying that we're using the spherical model of the electron, but it's known not to work. It's just kind of a apology. Well, take Dave Bergman, he got the idea, and I helped a little bit. Take a spinning circular toroid of charge, then you don't have this problem. The problem with the reason they add this extra mass in Howard's paper is to make E equals mc squared. E equals 4/3 mc squared. And but with a Bergman-Allen electron spinning charged ring, a model of the electron, it's an equilibrium due entirely to electromagnetic forces, and E does equal mc squared. So that's a huge problem right there. He's already in trouble.
We go sometimes weeks and nobody comes to me. I'm like, okay, well, I gotta go back to my doctor.
Very good. Ian, can we go ahead and proceed with the rest of the slides? Ian?
Yes, I'm here. I was talking, but I was mute. So just give me a second because I have to get the folder. I'm sorry for this, but I will get it eventually. The slides. There we are.
Because I think we're almost finished with the slides.
Oh, you say we're finished with the slides, David?
Almost. No, it's toward the end. We're like point number 6 or something.
Okay. The thing has gone back to the beginning. I'm sorry about that. Let me see now where we are. Where were we? Were we here or further on?
Let me read point number 5. Okay. Point Point number 5, Kowick summarizes the results of his monograph in the abstract of the paper labeled Summary. Kowick attempts to correct Maxwell's work, who missed the connection between electrodynamics and Newtonian mechanics because the experiments needed the required experiments needed very high precision. But this is only of interest to a few people. However, along the way, he tries to show that the electrons flowing down the wires, magnetic fields, show that the electrons flowing down the wires, magnetic fields are entirely due to their spinning and not at all to their flowing. Whereas today it is thought that there are two sources, the charge flowing and the electron spinning, with the former much greater than the latter. It is this that interests us as we attempt to show that it's the latter only, not the former. And we will continue in further talks to introduce the Bergman-Allen electron model that will considerably help with this endeavor. Okay, I think we talked about that, and Dennis showed a little picture. So let's go on to point number 6. We now introduce and utilize the fact that the electrons flowing down a straight cylindrical wire are actually apparently moving in a helical trajectory with axis of symmetry corresponding to the center line of the wire and with a torsion small relative to the radius of curvature. This is discussed in the one-page article by Achilles referenced above. Yeah, so I think we saw that. So let's go to point number 7. We conclude by considering the paper by Kowick referenced above. On the bottom left-hand side of page 164, in section 5, Kowick discusses the electromagnetic mass and conduction charge of a current circuit. On page 165, on the bottom left, Kowick admits difficulties which he tries to resolve by completely disregarding all the free electrons' very slow average drift velocity. And instead, Kowick relies on an extremely small percentage of the free electrons moving at the relativistic velocity, about 1/20th the velocity of light, which here I call that c divided by 20, in order to get his derivation to match reality. We suggest that the inertial mass gain discussed previously in this talk solves this discrepancy without requiring electrons traveling at such extremely high speeds. High speeds near c divided by 20.
Yeah, if you turn to page 165, Ian, on the lower left-hand side, we can get down to discussing that. Yeah. That's not the right page, 165.
You got page 161.
Yeah, my apologies. It's just taking some time for me to get all the files together, but I know exactly what I want. It's going to take a moment or two. Just a second.
Oh, that's fine.
Uh, 165. The bottom left, I think you said. Is that it?
Yeah, I think so. He does a couple of examples. We're interested in example 2, which is B, because A and B. The second example is labeled B. A toroidal coil of ring radius capital R is 10 to the minus 1 m, where m is the mass of m sub s is. Oh no, it's m. Sorry. Meter, must be meter. 1/10 of a meter. Mean turn radius, little r, is 2 times 10 to the minus 2 meter, with n equal 1,000 turns and carrying a current of 5 amps. The inductance L he gives a formula for it. It looks like it depends on the resistance, R, capital R, but capital R here is actually the mean turn radius. Its mean is the ring radius, excuse me. The little r is the mean turn radius. So L does not depend on the resistance. It looks like it does. And he gives some numbers for these, and he's 8 pi times 10 to the minus 4 Henry is the inductance. And the internal flux density is about 1/100th Weber per meter squared, or 100 Gauss. Length of the wire is 40 pi meters. So he uses a formula he's calculated on the previous page, and comes up with a mean velocity of 1.76 times 10 to the 7 meters per second, or in other words, about 0.0585 c, or 1/20th, about the speed of light. Okay, now that's got to be changed, because the drift velocity can be measured indirectly, and it just up in the top of this column, on the same page on the left, he talks about Fermi-Dirac statistics, and root mean square velocity of free electron in copper is 1.6 times 10 to the 6 meters per second. But Fermi and Dirac did not know about Neo-Newtonian mechanics. And so I rather interpret this as the inertial mass of the electron gaining inertial mass according to Neo-Newtonian theory, and I work out an example and solve for the value of multiplier times the mass of the electron. And that seems to be the, I think that's the last slide, last file. Ian, can you bring that up?
I won't.
Just while I'm doing that, there's somebody talking in the background. I'm trying to find out who it is.
It's not here. It's not here.
No, I know it's not you. It's a female voice. So maybe it might be Slobodan, who came in just now. He's muted, so I'm not sure. It couldn't be Jim. I don't know who it is. It's not you, one of you guys. Anyway, you want the slides back, do you, Denny?
No, I want the last file of the 8 files I sent you.
The last file. I may not have them in order. Was that your own key data, or
Well, what?
was it a Colbeck calculation 4?
Yeah, key data 75.
Key data 75. Quite, yes. Is this it?
Yes.
No, I said yesterday too, because I said.
No, this is not. I'm sorry. This is not the right one. I'm trying to.
What do you want?
I think it's the 8th slide. Is this the 8th slide of the 8 slides?
Well, I may not have them in the same order as you, but I have them entitled. I'll just bring them up now.
Well, if they went in the same order, it would be the last one, I think.
Okay, I'm not sure they're the same order, unfortunately. The last one was the slides, actually, version 3. Neo-Newtonian parts 1 and at 23. What's that? That's your book. That's not what you're talking about, no?
No, that's not it.
It is. Okay. Colbeck calculation, is that it?
Yes, maybe that's it. Okay, I think so, yeah.
Okay.
Let's see. Yeah, here I start out by computing the drift velocity in a copper wire of a diameter 1 millimeter, which is, I'm just basically repeating the Colwick argument that we just discussed. And Colwick says he doesn't say copper, but he says copper up above, so I think he's thinking copper. So the formula from Wikipedia is 1 over n, little n times capital A times lowercase c. And using this formula, I get drift velocity. Can you move down, Ian? Oh, okay, it's number 6. No, number 8. Number 8. It's the drift velocity is 0.000468, which is 0.468 millimeters per second. So it's not, the drift velocity is very slow. It's not up to 1/20th the speed of light. Okay, so slow down a little bit more. And let's see here. We're solving for the multiplier F times m0, which gives the right drift velocity, which is what we've just calculated, as, which I just mentioned. And scroll down a little bit. We solve, and for F, okay, a little bit more. We're solving for F there in 16, 17. F is equal to, wait, okay, stop. 3.75 times 10 to the 10th power. That's, in other words, the electron has multiplied its inertial mass by a factor of 10 to the 10th, roughly, which is surprising because, you wouldn't think that could happen. But the thing to remember is the electron mass is 9.11 times 10 to the minus 31. So the acceleration, using Newton's second law, the force over the mass, which is essentially 0, is equal to acceleration, which then must be essentially infinity. So that's why it's possible to hike up the pseudo mass, and so the R mass, without changing the rest inertial mass, to such a, even just trying to find the drift velocity, you have to extremely expand the inertial mass of the electron, which, as I say, is practically 0. So if you're talking about multiplying something by 0, it's still about 0. So we have now calculated the mass multiplier, which is F. So the question is, all right, we've got this. Now that's fixed. The F is fixed. The mass change function is fixed. Excuse me, but we've also got to get all the conduction electrons in here instead of just a tiny fraction. So we just gotta hope that we get the right answer here. Otherwise, we're out of luck. Well, it turns out we do get the right answer. Could you scroll down a little bit? So using the value of F we've computed, we calculate the number of conduction electrons divided by the number of free electrons, which should be about 1. Yeah, unity. Oh, let's see here. Okay, scroll down a little bit more. Okay, smart. Okay, so here we go on number 11. We have the ratio of the number of conduction electrons corresponding to our F that we've just calculated. And below is the total number of free electrons, 1 per atom of copper. And the result is 0.785, which is about 4/5 of the conduction electrons. Instead of 100%, we have like 80% or 79.5%. But, this is acceptable because the drift velocity formula is not all that accurate. It's not, the drift velocity isn't really nailed down that well. And also, we've got a toroid mounted here, which affects the inductance. It drives the inductance way up because the toroid is an inductor. And there's no capacitors in this work of Cohen, just inductors. And so 4/5 is acceptable. Since, if you had a different size coil or something, you get a slightly different result. So this is quite a bonus. That's we'd already computed F as about 10 to the 10th, and now that value of F gives us basically the right answer here for the number of percentage of conduction electrons to free electron. The fraction of, not percentage, the fraction of conduction electrons to free electrons available for conduction. So we seem to be able to repair this part of Kullwick's argument where he sort of went off the rails and had to use Fermi-Dirac statistics, which are suspicious because if my theory is right, the Neo-Newtonian theory is right, then those statistics have to be recalculated. So so there were these three problems with Kullwick's theory. One was that he was using a spherical model, which he, to be honest, since he was an honest man, he had to admit that was extremely shaky and it was not stable and so on. Then the next was electrons flowing down the wire spiral down the wire. They don't just go down the wire. And you have to have this to get the magnetic field circling the wire as a concentric circle. And then the third one is that he had to have his electrons traveling about 1/20th the speed of light, a very small portion. And that's really quite far-fetched. But whereas if you introduce a variable inertial mass, then you can make some sense out of all this. So that's about it, I guess, for the Kullwick thing. Where are we in the slides, David?
I think we're finished now.
Okay, well, what time is it? Yeah, maybe we better go to questions and answers.
All right. So I'll bring this down. Thank you very much. I didn't want to rush you, gentlemen, but actually, yes, I don't have the. My understanding is that we've penciled in some further sessions. This is part one of what I think may be a 3-part session. So
yeah.
I thought we might be in a position, to deal with a lot of questions which will come later in the subsequent sessions. But anyway, let me close down what I have now, so at least we. I don't know if you want to go back to the slides, but see now. Close this this thing down. So I get control of it again. Okay.
So, Dennis, can you just tell us again how to get copies of all of your calculations? And
Well, I'm hoping that I can impose upon Ian to send all 8 files to anyone who emails them. Can I ask you to do that, Ian?
You have asked me to do that, and I've accepted, with happiness to do so. So, but obviously it's difficult just to send everything out to the world and his wife. We'd need maybe some sort of server. But if anybody wishes to send me an email, either through the CNPS or through my own email, iancowandr@gmail.com. For any of the slides, I'll just summarize them now. I can send them to you. Sorry, the files are, there are 8 files altogether. The first one, not necessarily in the order that they were shown, is the Achilles paper, which is a reprint from Galilean electrodynamics. I understand. It's let me see, I have it up here. Let me see now. Be nice to get rid of the top banner. Okay. Difficult to get that. Yeah, okay, here it is. So that one. Yeah, okay. Sorry, a bit of a mess here. That what I have on the screen is not actually capable of being moved on. I have to put it onto my desktop. But anyway, it's Galilean Electrodynamics, Volume 21, Number 6. It's correspondence. So it's a small article, but that's available. And if you can't get it, I'd be happy to send it to you. The next one is what was this? Did we refer to this? That's actually Denny's own revised Dimitriev's first heavy brass rotor experiment. So that's I think this is your own analysis using perhaps a program such as Derive 5. So that's available as well. The Kullback calculation is Denny's calculation, which I think he's referred to. Again, using the program and looking at the drift velocity and so on. The next one is the Kullback paper itself, which is 1955. Again, I'd be happy to send them if you can't get it, but it's a monograph number 150, and it's let me see where it was published. I had the reference here. It's paper was first received. It was published in the Institution monograph in September 1955. Okay, so that's a fairly theoretical paper. There was another thing which I think you didn't refer to, gentlemen, today, at least directly, but you asked me to include this in the 8 diagrams. It's the gravitational induction by Dimitriev, Open Access Journal of Physics. I think that's generally available. Volume 5, Issue 1, 2023. Okay. And then the key data, which was another one of those calculation sheets. So that's available. Further commentary on Dimitriev's 2023 heavy brass rotor experiment. So this was a reference, I suppose, but that's Dennis Allen's own analysis. And then we have what was this? Newtonian. That's a book actually, which you've published with Jeremy Davis.
Well, it's not It's not yet a book. This is a revised version of the last issue, which is available. But you should
Okay.
wait until.
Well, you're very kindly making that available. It's quite a long,
By the end of next month.
132 pages. Okay.
But the last published edition is the 22nd, but that's been revised a little bit.
Revised. Okay. So just say people wanted the book, even if it's not the most up to date one. Where would they get that?
Amazon.com.
Amazon.com. Yeah. Okay. Dennis P. Allen Jr. and Jeremy Derry Davis. And finally, the slides, version 3 is the most updated. The slides, I take it that those are available if people want them. But obviously, this talk will be recorded and the recording. See, you might like to look at the recording actually after the talk is finished. And if you need any of these documents, do not hesitate in contacting me, and I'll be happy to forward any copies. So let me get rid of what we have now. Let me try to get the discussion back, because it's been a little difficult getting all these things up simultaneously. Let me see now. I don't seem to be able to get rid of this. Yeah, okay. StreamYard. Okay, I think I'm back at StreamYard. I don't know, maybe minimize, maybe. No, it's no use. I have to get back so we can have a bit of a discussion here, gentlemen. That's possibly it. So if I have to get rid of this file there. Okay. Well, what I'd like to do, if you just give me a couple of minutes, there haven't been many questions coming in on the live stream, but I will just check them because I haven't been able to keep an eye on them. The potential between charged objects, both large and small, is how we get motion in the universe. So I'm not sure if you have any comment on that. Okay, at least I've got rid of that. That was just a comment. Cornelis has actually asked Dennis a question here, which I might just put to you quickly, if I may, Danny. He says, what record are you referring to when you say mass changes with different direction of acceleration?
That was a slip of the tongue. Different directions of velocity. Of course, acceleration leads to velocity. But the thing is, if something is going, let's say, 9/10 the speed of light in a certain straight down in a certain direction, and then it's accelerated a little bit to give a higher mass, the mass increases according to the gamma factor, if it's accelerated in the direction of motion. But if it's accelerated to the side at 90 degrees, the velocity increases then too, but it doesn't increase according to the gamma factor. It's some other factor. I forget exactly what it is, but it's not gamma anymore.
Gamma's the Lorentz factor. I think they asked that as well somewhere here. Okay.
Gamma is square root 1 over the square root of 1 minus v squared over c squared.
Okay. I don't know what this is about. It's sort of a skin effect or something. He said Shockwave says current does not flow in the wire; it flows along the surface.
That's a skin effect, but we're talking about direct current here, not alternating current.
Okay. Well, Those are the only questions that have come in, and I'll be inviting people from the green room. I'd just like to say this is a fascinating subject, actually, and I'd like to spend a lot more time looking into it. But this whole reversal maybe of the concept of the electrons flowing and giving rise to a magnetic field, and you're talking about the magnetic lines from the spinning electrons being the primary element. And then you also talk about a non-spherical electron. What is that? Does that tend to be an ellipsoid or something like that?
It's a torus. It's a torus of charge.
Oh, yes.
It's spinning at the linear velocity of light.
Spinning at the
linear model that we cooked, Dave Bergman and I cooked up mainly.
Yeah, I was going to say that. Yeah, Bergman and you have published in Common Sense Science on this.
Yeah.
Okay. And I noted en passant that, you talk about a mass equivalent 4/3 times the mass. So you get something, m is equal to 4/3 E over C squared, which would give equals 3/4 MC squared, which actually is an equation which came out of some of my own analogical studies. So it just spurred me to think about that. But let's see if there's anybody in the green room who wishes to come in. Now we've had we've had Jim Keane, we've had Slobodan Nedica actually is come in and out a bit, and we had Vladimir Nechitalo, but I think he's gone. Nechitalo. Cornelis has entered as well. So there is a little time left. Don't worry so much, because with the indulgence of our eminent speakers today, there will be time in the further presentations to go back onto some of the things which have arisen today, because they're fairly basic. But we have a little time. So if anybody would like to come in immediately, I'll bring him in. If not, I'll actually bring him in myself. So let me see now. Cornelis, you've just come in this minute now, and you were obviously listening to the presentation. Have you any comments or questions for the speakers? Actually, you're mute. Oh, you're here. Yeah.
No, I just got my microphone working again.
Perfect.
So, no, I was going to ask Dennis if he has a concept of what the characteristics of a static electron is, if it's not moving.
Yeah, it's a spinning ring of charge, and the whole thing has been worked out in 3 articles published in Common Sense Science, which I could send you if you'd send me an email with so I know your email address. Mine's Allen's, ALLENS, 51s @gmail.com.
Okay, well,
I'll send, it's been written up, and it's been checked, and it's in equilibrium, only due to electromagnetic forces, and it shows some remarkable things, really. I do say so myself. But it's all been worked out. And the thing is, I know you talk a lot about particles being wave patterns or something, right? Is that right? Is that
right? Yeah, that's correct.
Okay. In other words, vibration patterns. But you have the vibrations, but you don't have the vibrator. The vibrator, in the case of in many cases, is the electron vibrating. Well, how does it vibrate? Well, it could, the small radius could go up and down, or the big radius could go up and down, or it could become an ellipse and then an ellipse in the other direction. So in other words, using a good system of electromagnetic theory and this model of the electron, you get not only the vibrations which you have, but you get the vibrator too.
Okay, I have the vibrator as just a breather in the field.
Well, I think you have better luck with our vibrator, but that's just a guess.
Yeah, I'd have to see. You have documentation that kind of goes into details on that, then, or images.
We haven't. Yeah, okay. Well, send me an email at Alan's 11111
Oh,
at Gmail.
I think you probably have it on the list if you just
yeah,
put in DENNIS. But
Yeah.
by the way, Professor Hallam Bhutia just said, if electrons are rotating magnets, what are positive charges?
Well, they're modeled in Dave Bergman's and my theory as spinning rings of positive charge. Electrons are spinning rings of negative charge. In modeling, you have undefined terms, and then you have axioms or postulates concerning them. That's what's called
Yeah.
a model. And our model has a positive charge and a negative charge, but not both in the same particle. And it uses Coulomb's law and the Lorentz law of force. And so that it's when you ask what is a positive charge, you have to refer it to a model. You can't. I mean, you have to explain it in some terms, and the terms you explain it in have to be related to something that you can deal logically with, like our charge is the pressure on a certain point in the charge is due to Coulomb's law and Lorentz law of force. In other words, it depends both on the electrostatic field at the point you're interested in, and also the magnetic field at the point you're in, and the velocity, because the velocity comes in to Lorentz law. So you have to know the velocity of the particle. So that's our model. There's no way
You've published quite extensively on this, Denny, with David Bergman. I think in Common Sense Science, I'm not sure if the information is available elsewhere, but I understand that was produced by Bill Lucas, and it's probably not being produced now. But anyway, you've offered to send out anybody who requests from you.
Yeah.
It's quite interesting. And you have a number of articles actually in subsequent issues of that document.
3 articles. We had a 4th one, but there's an error in the 4th one.
Okay.
So Dennis, I didn't get Dennis's email address, and I know mine is.
I thought
mine
you
is
had it
the
on the list.
Well, he's not. I looked in the members list, and I don't see him in the members list of the emails I get.
Do you want to give me your email?
I tried to become a member, and I couldn't get the. I said to Dave DeHilster, I'll send you a check. He said, no, I don't want a check. Sign in, and we'll get you signed up as a member. Well, it didn't work. I tried to become a member, and it wouldn't accept me.
Oh, okay. I wasn't.
What I meant is, if I in my email system, it seems to recollect messages which have come in. If I just put in DENN, it'll automatically give me some prompts of emails I've obtained over the last number of.
Well, let me give him my email address again slowly.
Yes.
Pencil?
We'll just add you to the list on the emails that are sent out, because there's an email sent out giving us, for instance, the StreamYard link, and your name is not on that.
Okay.
Well, I think that's when he tried to get his name on it with David, and he hasn't succeeded, unfortunately.
And well, I think anybody can add a name to that list, and
Okay, ALLEN.
Yeah.
S is in Samuel at gmail.com. Oh, wait, excuse me. ALLENS and 5 1s at gmail.com.
And 5 1s?
Yeah.
11111.
Yeah.
Okay. Because I know you have more than one email address. So
Yeah, I used to use my Yahoo all the time, but they're doing strange things on there. It runs extremely slow.
Well, I'm
okay.
particularly interested in the document you might have that describes what you see as charge, because that's part of what I'm trying to describe as wave patterns is the charge, and the electron is just a mass in charge. So I'd like to compare and see what we've got there.
Okay, that sounds good.
Okay,
So-
well, that would be certainly very fruitful. So, can we leave it at that? Unless anything quick, Cornelis.
No, I'm good. I'm good. Thanks.
Okay, thank you very much. Thank you. Now, let me see. Actually, Slobodan, we haven't seen you for a while. Have you any? Have you any contribution or any comments or any questions?
Yeah, sure. Actually, I would support this kind of aspect of magnetic field being result of the kind of spinning of electron, rather than of electrons of drifting of electrons. Drifting of electrons contributes only to the dissipation. But I think it would be regarding these questions, what the charge is, what is negative charge, what is positive charge. One cannot say just simply, the electron is toroid of negative charge or positive charge.
If an electron is negative charge.
Toroid,
Yeah, negative or positive, because actually the charge itself is the result of the flow of the ether forming such toroidal vortexes.
Well, you have a different model than us.
Yeah, based on Tchaikovsky ether dynamics, actually, this kind of mechanics of fluids, and those flows go in both directions, equatorially and torally, and the interaction of first one is manifested as electric field, and of the toral one as a magnetic field. And then it just depends on the direction of those flows, whether it is positive or negative.
Okay.
And
Your volume is a little low, Slobodan. A little low.
This, sorry?
Your volume is a little low. We can hear you, but it's not too loud.
I think the electron should be looked at as a formation of flow of ether. So ether flows. You
didn't say anything about that, gentlemen.
I've been sending some materials. It had even one presentation a long time ago, based on the Tchaikovsky ether dynamics. And regarding this kind of increase of mass of electron, it is actually just the fluid mechanical effect. There is no essential increase of mass, but just when the electron moves faster, the reaction of the surrounding ether is such that it creates counter force. It doesn't allow electron to accelerate as it.
So you're just basically saying that the force varies, are you, rather than the mass?
Yeah. So there is no like change of mass. So I mean, the Lorentz factor and anything like that should be kind of irrelevant here. And current and magnetic field itself, actually, there was one comment. Current is actually flowing around the conductor. Not only the skin effect, but actually with DC excitation, the same happens. The so-called Heaviside strange energy flow, and I think Ampere also had such experiments. An interaction of conductors longitudinally, not only transversally. So I mean, with such kind of conceptualization, many answers can be, many views, concepts should be supported and further extended. In particular, what is the charge? What is the magnetic field? What is the positive, negative, one polarity, the other polarity? Everything should be actually the flow of ether. So concept of spin of electron as a rigid body, charged negatively or so, is kind of too simplistic and doesn't correspond to the reality. And one takes the aspects of fluid of mechanics and considers the formations of ether itself within ether, then actually many things can be cleared, including these effects of kind of gyroscopic effects, decrease of mass or whatever. It is just interaction of those structures with the surrounding ether. So that actually gravitation, that is the gradient of inflow of ether, somehow be modified by the very rotations and the dragging of the ether by those formation and those structures and their rotation and so on. Okay, that was something that I wanted to.
Okay. You have different models, but I'm not sure if they're at variance with each other. In fact, they may be complementary. Have you have any response, Denny or David? I bring David up now as well. To this whole concept of ether and ether dragging and all that sort of stuff.
Well, we hope to use the Bergman and Allen electron modeling and proton modeling and positron modeling to quantify the positron electron ether. We hope to instead of just qualifications qualitatively, we hope to quantitatively deal with the positron electron ether that David Thom champions. But he has to have that the positron and electron are circling each other so that the centrifugal force keeps them apart. We're hoping to be able to correct that by an actual model which we can then compute numbers, not just tendencies. And we're hoping to show that you don't need, positron and electron do not need to be rotating about each other at high velocities so that the centrifugal force will keep them from being annihilated with each other.
But the rotation is kind of something that is kind of a misconception, or actually something that has some deeper process beneath it. So it is actually the flow, and the flows in ether interact among each other based on the pressure of that rarefied gas of the ether, and then things becomes physical, and kind of really explicable, and this kind of refinement of the results that I support. I said based on the ether dynamics of Pachukovsky and also Jean Clément. Jean Clément had claims and did some experiments.
Yes, we've had him on.
So it's not the flow of electrons that causes magnetic field, but they are spinning, and so actually the application of electric field tends to align those electrons and their spins actually, or their axis, and then the net effect of the magnetic field and the current flow around the conductor results. So all this is based on the general heterodynamics of Dr. Astyukovsky. And on my ResearchGate and Academia Edu pages, there are a couple of translations of that book. So if you search with Astyukovsky and my name, you get maybe some.
Pardon me, is Otovsky still around, or?
Astyukovsky died 4 years ago.
Okay.
What is the name? What is the second name we need to look up? Netic and what else?
Atsukovsky, Atsukovsky, say.
Adjukovsky.
Atsukovsky, yes.
You're converting from the Cyrillic to the Roman. Okay, that's close enough, no doubt.
Okay.
Okay. By the way, Cornelis is just referring to Ron Hatch as well. Dennis, if you want to check, Ron Hatch had a similar model of the electron when I spoke to him in his book that he supplied me with. You're probably familiar with that, actually.
Well, I have his book. I didn't realize, I haven't read the whole thing. Maybe I missed that part about his model of the electron. But
there's
the
there's another interesting phenomenon which I would like to see if we could link all this to. Have you ever heard of the expression Zitterbewegung?
Yes.
Which is supposedly an oscillation of the electron, which is found in quantum mechanics. A lot of people have done extensive research on Zitterbewegung and different models of the electron. I would like to see how the model that Dennis came up with can correlate with this Zitterbewegung model.
I don't know. Dave enlisted my efforts because he was having trouble getting his numbers right. Like when Sabovin talks, he's talking about tendencies more than numbers. But when you go to calculate things, you need numbers. And so he enlisted me, and I reduced the problem to this Bergman electron model, which you could then, calculate numbers for. If you want to know what the whatever property you want, that'll allow you to actually calculate it. And the thing about our model is that, if, for example, it tells us things like, what if the electron mass, the classical electron mass, were actually the mean of a distribution, which had a small standard deviation relative to the mean? Would that work in our model? Yes, it would. Similarly for a proton, what if the proton's classical mass were actually a distribution with the classical mass as the mean, and standard deviation is small with respect to the mean? Questions like this might be answered by, if you're good at statistics, with the experiments that have already been done. You might be able to introduce this idea and calculate things to a better accuracy, assuming that the thing is just a mean, the mass is just a mean with a small deviation. Also, we found out that the inertial mass and the gravitational mass are disjoint as far as physics is concerned. The inertial mass is the integration of the magnetic field over all space, inside and outside the spinning charged electron. Then the gravitational mass is divided by c squared, and the gravitational mass is the integration of the electric field over all space, divided by c squared. So the actual inertial mass is half the Newtonian mass, and the actual gravitational mass for electron not traveling very fast is half the inertial mass of the classical inertial mass. And so then the Newton's second law would be that m sub I, this new inertial mass, which is half the regular one, times 2a. The factor of 2 coming in because you have to get the same answer at the end. Similarly,
what's A? The radius?
What?
What's A? You said 2A.
Acceleration.
Oh, okay, right.
Because, it's a matter of scaling. If you half the inertial mass, you have to double the acceleration to get the same answer.
Okay.
Because F equals ma. And if m is half, then A has to be twice.
Okay, proportional. So, Slobodan, can we leave it at that for the moment, unless you have anything very, very quick, because we're running quickly out of time. But we hope to have you back at the next two sessions where we can delve into some of these things.
Show this book. I mean, like,
that's Otovsky, is it?
yes. There is guy, Dmitry Osenilo, who kind of continued this work. Kind of modifying something, but I don't think it's necessary. Of course, there are many things to.
Okay. Is it in Russian, the book?
Yeah. This is
okay.
Russian. I translated some sections,
You've translated some sections, have you? Okay.
Some sections.
Well, thank you, Slobodan. Thank you very much, and we'll hope to have you.
Send
back
me email
again.
if you something. I was presenting this earlier and kind of commenting.
What about email?
So my email is first goes family name, NEDIC.
Yeah.
Dot and then consonants of my first name, SLBDN.
Okay.
SLBDN.
SLBDA.
So
Consonants only.
Dot SLBDN at gmail.com.
At gmail.com, yeah. Actually, my email system seems to recollect or remember anything. So, in correspondence with you in the past, if I just typed in NED, it probably would come up with your name. But okay, thank you very much. We'll talk to you again at the subsequent sessions. Just one or two things have come in. Nullius in verba, I couldn't avoid noting that. He hasn't made comments before, but that's the motto of the Royal Society, nullius in verba, which means nothing by words, or actually it really means take no man's word for it. If somebody tells you something, check it yourself. So nullius in verba has said, we can reproduce all weak fields prediction of GR with Maxwell, Snell, and Fermat. It's not ether per se. It's just the property of the vacuum. Permittivity and permeability works simpler than GR. He's made a number of further things. He says search for GUCE, classical unified gravity, electromagnetic. SR is also doing the thing. He's worked on this, he said as well. Okay. Well, we're coming near, I'm not sure what that is. We're coming near the time when we just have to devote a moment or two to allowing, Carl Reef came in for a moment there, but he's gone off again. What we normally do, gentlemen, is we give either or both of you a minute or two to summarize today's session, maybe to repeat some things, or in the light of the discussion and questions and answers, if anything has arisen in your mind that you'd like to stress, we give you a few moments each to say your own, or if one of you wants to say it on behalf of both of you. And then I'll come back and officially close the meeting. So I'll say nothing either praiseworthy or in condemnation until you've made your summary. So which of you wants to do that? Shall I put Danny up? And if he wants to bring David, then I'll do that. Shall I do that?
Yeah, that sounds fine.
Well, it seems clear that if Colwick is actually right in his deciding that the magnetic field of electrons going down the wire is not due to just charge going down the wire. Instead, it's due to the charge is spinning and having spin magnetic fields. Then this would be a big surprise, I think, to the people working in this field. And of course, just because we can fix the three main problems with his theory up, doesn't mean that's right. It has to be experimentally determined. But it seems to me that he may have something here. And if you introduce variable inertial mass, according to Neo-Newtonian theory, you get you can figure out in the Bergman-Allen electron model and the Achilles changing of Maxwell's equations, then you get something which is like able to stand alone. It's not far-fetched like his paper is, unfortunately, and that's why it never was accepted in the field. It was 1955, and it never caught on. And if this could be, that would be a really good application of Newtonian theory, which hopefully would then have to be taught in universities because people in industry were using the theory and they needed courses to educate them in it. So from that point of view, we think that this may be a very fortunate thing for the Kullwick manuscript, which David came along and was analyzed according to Neo-Newtonian mechanics.
Okay, very, very well. So, David, I'll just give you an opportunity in case you want to add anything or not. So, I shall just bring you up and give you an opportunity.
No, I think Neo-Newtonian mechanics, based on my study, is very worthy of further investigation and calculation. I am totally opposed, though, to the concept of relativistic mass and mass increasing with velocity. But I do think that what Dennis is onto is very worthwhile. By the way, a lot of physicists are abandoning the concept of relativistic mass or mass increasing with velocity. It's almost been abandoned.
Okay, you didn't hear what I said there because I hadn't been on. I said thank you very much for that supplement. So it devolves upon me now in the couple of minutes we have left to express our deep gratitude to our two speakers, Dennis Allen and David Bauer, for having come together. I think that they've been rather complementary in their skills and in their endeavors. They've made a very good team. David has been responsible for making those very, very clear slides, which really summarize everything, and I think can be used as a basis for what has been said today, because there's a lot of material there. And the Kullwick paper itself is quite a detailed paper, and it requires quite an amount of study before one goes on to see what Dennis and David have been basically doing by applying Neo-Newtonian mechanics to this problem, which doesn't seem immediately resolved in regard to looking at conventional means of electron drift velocity and all that sort of thing. So they've got us thinking, they've got me thinking, and I look forward to the next two sessions. I have twisted their arms a bit and persuaded them to devote a considerable amount of time because you couldn't get through all this material actually in one session. So luckily we have 2-week breaks in the meantime. This particular one actually was postponed by 2 weeks to give more time and so on, but I was quite happy to do that. So we're hoping maybe I think throughout the month of April to come back to this, and I'd like to thank both Denny and David for the detailed amount of work that they have done and for the patience that they have displayed in explaining these complex issues to us. Actually, they've been working on these things for years, and we've come upon them suddenly. Cornelis has asked, can we get the material in advance of those sessions? Well, I might just ask Denny that. So Denny, Cornelis has asked, can we get material in advance of the next sessions? So I suppose what I'd like to ask is the next sessions, will you be relying upon these 8 documents that you've already supplied me with, or will you be dealing with other documents? Do you know yet?
Yes, we'll be dealing largely with other documents on Bergman-Allen electron modeling.
So I think what I'd say then, if I may, is that unless anybody wants some of these documents from today, contact me and I'll send them. But let's wait until the next 2 sessions. And again, a similar principle will apply. The documents will be available on request. So I hope that's all right. So thank you very much, Danny. Our gratitude is very, very, very great to the 2 gentlemen for having taken the trouble for explaining these details to us. I'm looking at some of these comments. So, sorry, but not being shy of expressing the complex issues that they've been dealing with, and yet in a somewhat contradictory fashion, explaining it to us in a way which is easily digestible. And I think that's really what we need on a Saturday. For 2 hours, we devote ourselves to these questions, and we're dealing with questions that maybe some of us haven't thought about before, or maybe are related to other issues. And I think today has demonstrated that very much. So thank you one and all for your contribution. Thank you very much for the comments. There weren't many comments coming in on the social media. I think we've sort of blinded you a bit with science, but the ones that came in were quite to the point. And thank you very much for your contributions in the green room. We didn't have too many people today, but I think we may even have a bit of a post-mortem on some of the internal discussions we have. I think people may have been watching it and yet not participating in the green room. So the time is caught up. I must stop now. I'll wish you all, wherever you are, a very good day, and renewed appreciation and thanks to our 2 eminent speakers. Good day to you all.